Okay, so now we'll talk about differential K-forms, which essentially combines the ideas of differential one-forms and linear algebraic K-forms that we saw in the last two videos. So if omega is a differential K-form on Rn, then what this means is that with our space Rn, at every point P, we'll have omega P, which is a K-form at P. And so what that means is that we have k different vectors, v1, v2, all the way up to vk. And we can evaluate, and these all live at the point P, and we can evaluate omega p v1 through vk. And if we have a different point, p prime, then we might have different vectors, v1 prime, v2 prime, all the way up to vk prime. And then we have a different k form at the point p prime, where we can plug in these vectors omega v1 prime to vk prime. So if you're familiar with the language of tangent spaces, then this is just saying that you're taking k vectors in the tangent space at each point, and then you can evaluate a different k form at every point. And so alternatively said, what you can do is you can take k vector fields v1 through vk, and what you can do is you can evaluate omega on these vector fields v1 through vk, and this will give you a function. And so what this function is at the point P, so let's call this function, say, f of x or f of p. And f of p is equal to omega p, so the k form evaluated at that point, evaluated on the vectors v1p all the way up to vkp. So for example, v1 maybe looks like this at that point, and then it goes something like that, and then becomes v1 prime at the point p prime. And then maybe v2 is part of a vector field that looks like this, and you associate just vectors at every point, and this allows you to evaluate the k form on the vectors at each point. So what do these guys look like? Well, a one form looks something like dx, maybe y squared dx plus z dy. And so k form is essentially going to look like a product of these. So for example, we can have something like y squared dx dz plus z dy dz, and this will be an example of a two form. Or maybe we can have something like y z dx dy dz, and this will be an example of a three form. And so I should issue a warning here, which is that dx dy, something which looks like this, is actually meant to write dx wedge dy. But the reason that isn't is because these things have shown up in integrals before the language of k-forms was developed, and so the industry standard is just to leave out this wedge product. But what this means is that dy dx is actually not equal to dx dy, because dy dx is essentially a two form which says at every point p, take your two vectors v1 and v2, and then take the parallelogram spanned by them and project it down onto the xy plane, and then take the area of that. But then dy dx says that it has to have the opposite orientation. So actually dy dx is equal to negative dx dy. And you can show that every omega can be written in the following form as the sum of aix dxi. So here dxi is equal to dxi1 all the way up to dxik, and I is a multi-index, so I is a subset of 1 through n such that the size of I is equal to k, and this n is the dimension of the ambient space that we are working with. So this essentially says that, for example, every two form can be written in the following form, where you have dx dz, which would be dx1 dx3, dy dz, which would be dx2 dx3, and then you might also have something involving a dx dy. And so what are these k-forms actually useful for? Well, remember that the linear algebraic k-forms gave us a notion of volume, or linear combinations of volumes, on k-dimensional subspaces of your vector space V. So the differential k-form is actually like a nonlinear generalization of this, where you can evaluate it on a surface and or a k-dimensional subspace, and it'll give you some number. So maybe, as you can see by the notation that we have here, these things are meant to be integrated over surfaces. So if you have some surface omega k, so for example on Rn, maybe you have some surface which looks like this, and then what you can do is you can take an integral over some k-dimensional space of some k form, and you'll get a number. So infinitesimally, what it'll look like is it's giving you a linear combination of areas, which is what this is doing. But globally, it'll give you some numbers. And at this point, it doesn't really make sense to call it volume in general. So it's just saying that a differential K form is something which can be integrated, and it's something which allows you to find an integral. So I'll talk about how to deal with this in a bit, and I'll also give an example at the end to uh, clear up sort of all of the language that's been going on. But first, I want to talk about how you can construct some K-forms. So one way that you can just construct these differential K-forms is by taking the so-called wedge product. And this is really a construction going back to the linear algebra. And so if it's the wedge product is a map which goes from the kth wedge product times the lth wedge product, and then goes to lambda k plus L. And so the way that this works is, let's say that you have something like epsilon 1 wedge epsilon 2, which is a linear algebraic 2 form, and then you wedge that with epsilon 3. Then this will be nothing but epsilon 1 wedge epsilon 2 wedge epsilon 3. But remember, not every k form can be written in this. Sometimes you have to take linear combinations. And so what you can do is you have some linear combination like this, then all you do is extend by linearity, and you have that this is equal to this guy plus epsilon 1 wedge epsilon 2 wedge epsilon 4, and more generally for other things. I want to note that this is not necessarily a commutative operation, because epsilon 1 considered as a 1 form, wedge epsilon 2 considered as a 1 form, is not equal to epsilon 2 considered as a 1 form, wedge epsilon 1 considered as a 1 form. In general, they're so-called graded commutative, where omega wedge omega prime is equal to -1 to the KL omega prime wedge omega. And the idea is that, for example, if you took this case where k is 2 and L is 1, so omega is a k form and omega prime is an L form, then in order to change it from omega wedge omega prime to omega prime wedge omega, you essentially have to move this guy over each of these terms. So since we only have one term over here, we'll have to move this one guy over two other 1 forms. But if, for example, this had 3 terms, like epsilon 3 wedge epsilon 4 wedge epsilon 5, then we'd have to move each of these 3 terms over these 2 terms, and each time you have to get a sign flip. So until you'll have KL many sign flips. So now that we have this construction over the linear algebraic K-forms, we can extend it to a construction of these types of K-forms. So for example, we can do something like y squared dx dz plus z dy dz, and take a wedge of that with, say, dx. And so what will this do? Well, we get something which looks like y squared dx dz dx plus z dy dz dx, and this will be a 3 form. So now using the rules, because essentially each of these represents an infinitesimal 3 form on the tangent space, this looks something like epsilon 1 wedge epsilon 3 wedge epsilon 1 is equal to 0, because again you can swap around the epsilon 1s and get a negative sign. Whereas this one will look like epsilon 2 wedge epsilon 3 wedge epsilon 1, which you can move the epsilon 1 over. And so we see that this is the same thing as z dx dy dz. And because you move it over 2 different 1 forms, then the 2 negative signs cancel out, and you get a positive 1. So I want to mention that this sort of definition of the wedge product does depend on the basis that you choose and the dual basis that you choose, the epsilons in terms of the e's, as we had before. And you can define this in a basis independent way. That is to say that omega is a k form and omega prime is an L form. So you should be able to define a function omega wedge omega prime evaluated on functions v1 through vk plus l, because in total this should be a k plus l form. But the formula is a bit annoying to write down because this is not the same as omega evaluated on the first k and omega prime evaluated on the latter ones. And the reason that these are not the same is because since it's a k plus l form, something like epsilon 1, epsilon 2, epsilon 3, you have to permute the three vector entries amongst all three of them. So basically, you'll have some vectors mixing in between these two, and so maybe you'll have like some k plus 1 showing up here, and some like maybe v3 shows up over here, and you have to take the sum over all those permutations. And this is to avoid something like epsilon 1, wedge epsilon 2, wedge epsilon 3, if you evaluate this on E3, E1, E2. Well, these are the three basis vectors of R3, and if we're working in R3, then this should give us plus or minus 1. But if you just evaluate the first two vectors, or the first two forms on the first two vectors, and the one form on the third vector, then you will get 0 instead of plus or minus 1. So you have to write some annoying permutation formula. And so if you want, you can try and figure that out yourself, but I won't bother with it. So the last thing that I wanted to show in terms of construction is that the wedge prior sort of helps you build up k-forms, in the sense that you start with smaller k-forms and then you go up in dimension. But you can also go down in dimension by sort of plugging in vectors or vector fields. So the way that that works is, let's say that you have the three form dx, dy, dz on R3. So if you've done vector calculus, then you should know that this sort of looks like a volume form. And so what that means is that at the point P, if you have the vectors v1, v2, and v3, then dx, dy, dz evaluated on v1, v2, v3 gives you the infinitesimal volume spanned by these three vectors. So you can use this to compute a volume by saying, let's say that you have a three-dimensional region V, then you can integrate over V, dx, dy, dz, and get the volume of V. However, you can also use this 3 form to obtain surface areas. So for example, let's say that you have some surface that looks like this, and you want to compute the surface area of this living in some ambient R3. So what you can do is you can define a 2 form at this point P as follows. So first, take the normal vector to your surface n hat, and then define omega of 2 vectors to be dx, dy, dz, with v fed in as one of the vectors, oh sorry, not v, n hat fed in as one of the vectors, and the other two slots open. So what this is saying is that you feed in 2 vectors, and then this will take the volume spanned by these 2 vectors and the normal vector. And so what that does is, in essence, what we want to do is at the point, if we have a parallelogram tangent to the surface, then we want to compute the infinitesimal area of this tangent parallelogram. And if we take the integral of that area over the surface, then we should get the surface area. So how can we numerically compute the tangent vector, or sorry, the area of this parallelogram? Well, what we can do is, if we have something that looks like this, and it has an area of this, area of A, then numerically that's the same as the volume of the parallelepiped spanned by these 2 vectors and the unit normal vector. And so compute the unit normal vector depends on the metric that you choose, and that's why this actually does give you a surface area, which depends on the metric that you have. But through this procedure, you can start with the 3 form, plug in one vector, and so the normal vector at each point is going to be different. And so that's why this 2 form is going to vary from point to point, and it won't look like the same as dx, dy, dz. But then if you integrate omega over your surface S, then you should hope that this gives you the area of your surface S. And so I'll go over an example in a bit, which uses this to compute the surface area of a sphere, and hopefully that'll help clear out what all of this is saying. Okay, so I mentioned that k-forms are useful because they can be integrated over k-dimensional subspaces. So I want to formulate a way to be able to meaningfully talk about an integral over a k-form omega on Rn over a k-dimensional subspace sigma of Rn. And so this will be the notation for what it is. And first, I'll talk here about the heuristics, or sort of intuitively, geometrically, what's going on as the picture. And then next, I'll give an example of how such an integral is actually done. And it'll be to compute the surface area of a sphere, as I mentioned. So in order to motivate how to define this thing, let's go back to the case of a one form. So if we have a one form tau, then some curve gamma, then what we can do is we can take the integral of tau over the curve gamma, which lies in Rn. And the way that we do this is that we can parameterize gamma by some interval from 0 to 1. And this interval gives us tangent vectors, which are given by this parameterization of if this is gamma t, then these tangent vectors v is equal to gamma prime of t. So the derivative of gamma with respect to t. And so now that we have a tangent vector at every point in our space, we can feed that into our function tau and integrate that. So essentially, if we break up our curve into a bunch of small segments, then what we can do is we can sample points from each of those segments, call these points pi. And so this integral will be approximately equal to the sum over I of tau evaluated on gamma prime of ti, where ti is the value of t mapping to this point pi. And so as you take a finer and finer subdivision of your path, then this sum will approach the value of your integral. And I guess you should multiply this times the length of subdivision. So this is just like how you would normally compute an integral of a curve. And so in order to generalize this to a k-dimensional space, what we can do is we can parameterize a part of our surface via some parameter space, which will be a copy of r to the k, and we'll have coordinates theta 1, theta 2, and maybe in this case, the picture is just two-dimensional, but we can have coordinates all the way up to theta k. And so essentially what we'll have is this patch mapping onto this patch. And so now what we want to do is essentially subdivide our space into a bunch of little squares and sample points in here. And usually when you're integrating a function, what you do is you evaluate a function on each of these points and multiply it by the area of the function, and then sum all those up together. But over here, instead, we have a k-form. So we need to somehow get a real number out of a k-form. In order to get a number out of the k-form, we need to pass in k different tangent vectors. So similar to here, over here, the tangent vector was given by the derivative of the parameterizing curve, which is essentially given by the image of the tangent vector in this path over here. So similarly, what we can do is we can take tangent vectors over here, call it v theta 1, v theta 2, and so on and so forth, and then look at their images, which by slight abuse of notation, I'll also call v theta 1, v theta 2, all the way up to v theta k. And so now that you have k different tangent vectors, in this case I should really only have 2, but in general you'll have k different tangent vectors if your submanifold is k-dimensional. What you can do is at the point p, you can evaluate omega p times v theta 1 at p all the way up to v theta k at p. And so this will give you is k different tangent vectors which you can evaluate a k-form on, and this will give you a real number. And so you do this for, say this point is p1, p2, p3, p4, p5, p6. And so then you take the sum over I of this expression over here, and then you have to multiply it by some sort of an area, so that, for example, if you subdivide this into 4 pieces, then you'll be taking 4 times as many samples, but then the area cuts down by a factor of 4. So really what you should be multiplying this is by the amount of area in your parameter space. So that would be d theta 1 all the way up to d theta k. And so here, this can be considered as a k form on r to the k. It can also just be considered as intuitively as classically taking a little distance in the theta 1 direction, a little distance in the theta 2 direction, and so on and so forth. And then, so this integral, as you take finer and finer subdivisions, will approximate this integral omega over sigma. So this is sort of intuitively what's going on is that you have these k vectors, and then you push them forward to the surface, and then you integrate them with respect to these little infinitesimal volume elements, and then you get the integral omega. But another way to view this is sort of the dual perspective that we talked about in the one forms video, which is that this gamma prime of t really defines some equations x of t, y of t, and maybe you have some more variables. And then what you can do is you can write dx is equal to partial x by partial t dt. And so what this is saying is, as you vary t a little bit, how much does the x coordinate change by? And so now we have written dx as a one form on this space, which is R1. And now we can pull back our computations to doing things here. Okay, so now that you've expressed dx in terms of these guys, what you can do is you can write tau as being some function f sub x dx plus f sub y dy, and so on and so forth. And then when you take the integral over gamma of tau, you can rewrite this as the integral over gamma of f sub x dx, and so on and so forth, which you can rewrite as the integral over gamma of f sub x times the derivative of x with respect to t dt, plus the other variables that you have. And then here, now you're taking just an integral over dt, and all the other terms will also have an integral over dt, because y will be, for example, dy dt times dt. And then gamma just becomes this interval, which will be the integral from 0 to 1 of these terms. So similarly, what you can do is you can sort of take a dual approach where instead of taking these vectors and transporting them up to here, you can take the k form omega and transport it back to here. And the way that you can do that is on Rn, you have the coordinate functions x1, x2, all the way up to xn. And these parameterizations essentially define n different functions, x1 of theta 1 through theta k, all the way up to xn of theta 1 through theta k. And similar to what you do in multivariable calculus, you can define dx1 is equal to sum of the partial derivative of x1 with respect to theta j times d theta j. So this will look like partial x1, partial theta 1, d theta 1, and so on and so forth. Terms that look like that, d theta 2, d theta 3, d theta 4, and so on. And similarly, you can have expressions all the way down to dxn. And now your k-form omega, as we saw before, can be written as a sum of ai dxi, where I is a multi-index of size k. And then after you plug in these different substitutions, then you can express all these dxi in the form of some function times d theta 1 all the way up to d theta k. And then you take the linear combination of these derivative terms and these AIs, and then you get, essentially there's no sum anymore because there's only one k form on r to the k, and you get some f of theta. And then what you can do is you can just integrate that over the parameter space, and you can say that the integral of omega over the some manifold sigma is just equal to the integral of f of theta d theta 1 to d theta k. And this is over your parameter space r to the k. So now I'll sort of do an example of taking the surface area of a sphere, and hopefully all these words start to make a bit of sense. Okay, so finally I'll do an example of computing the surface area of a sphere using differential k-forms, which should hopefully tie everything together. So here's the unit sphere in R3. So it's a two-dimensional sphere. And as I said before, if you want to compute the surface area of this, one way to do that would be to take the volume form dx dy dz and then plug in the unit normal vector as an input. So as we saw before, any two form, which this is because it takes in two more vector inputs, can be written as a sum of dx dy, dx dz, and dy dz. So it's an interesting question about how you would do this, but if you spend some time thinking about it, and you probably should, you'll see that since you essentially need to permute each of the vector indices amongst each of these one forms, then what you should do is you should essentially pass in this first vector into each one of these one forms, and then keep the other two forms, two one forms open. So what I mean by that is you have dx evaluated on n hat with dy dz, and then dy evaluated on n hat, dx dz, and then dz evaluated on n hat, dx dy. But moreover, when you do this, you also need to take into account some of the signs that come along with permuting the vector components. So essentially that becomes equivalent to looking at how this has been rearranged if you were to sort of block off the vector. So because this is dx dy dz and it's in the original order, nothing changes. This one, dy dx dz, you swap the y and x, so this actually gets a negative sign. And then dz dx dy, because you move the dz over two of them, that's two negative signs, so this is just a plus. Now for the unit sphere, the normal vector at P, which is x, y, z, is also equal to the vector x, y, z. And so it's a unit vector because x squared plus y squared plus z squared equals 1 because it's a unit sphere. And so what we get from that is that this will be x dy dz minus y dx dz plus z dx dy. So what that means is that if you take two tangent vectors over here, then the infinitesimal area generated by them will be expressed by plugging in the xyz coordinates as the coefficients for here, and then plugging these two vectors into this two form over here to get the infinitesimal area. So in order to get the full area of the sphere, what we should do is we should integrate this two form omega over S2. So as I said before, the first thing that we're going to need is a parameterization of our sphere. And the parameterization I chose is a pretty standard one where you take theta and phi, and then you send it to these three functions. And you can check that the essentially the theta direction goes around in the unit circle in the xy plane, and the phi direction moves up and down here. And you can check that phi goes from negative pi over 2 to pi over 2, because if you plug in negative pi over 2, you'll get 0, 0, negative 1. Pi over 2 gives you 0, 0, 1. And then if you have phi equals 0, then this third component will be 0, and you essentially get the unit circle in the xy plane. So in terms of parameter space, we have these parameters theta and phi, which map to the unit sphere. And so if you're paying attention, really this is not the full unit sphere, but you're actually missing a little arc corresponding to the value that theta equals 0 and any value of phi. But because that's like a one-dimensional arc on a sphere, that doesn't really make a difference to the integral. And so technically, you'll usually need to split up your surface or k-dimensional subspace into coordinate patches, but a full description of the integral will await the abstract definition of manifolds and talk about partitions of unity. But for the time being, since we have this parameterization which does convert the sphere, we can use it to compute the integral. And essentially what these three functions are is expressing x, y, and z in terms of these functions, these variables theta and phi. So as I said, for the prescription of how to compute these integrals, the first thing we have to do is rewrite dx in terms of d theta and d phi. So the way you do this is take the partial derivatives of x with respect to theta d theta and the partial derivative of x with respect to phi d phi, and then you'll get this equation. So this will, again, the general formula of like why this is the correct thing to do, we'll have to wait a later discussion about something called a pullback. But it's essentially saying that if you take a vector over here and you look at how much does changing or moving in that vector change the x coordinate, then you can either view that as saying, look at the image vector over here and then evaluate that on dx, or you can say, look at the initial components in the theta and phi directions, and then take out these coefficients. Similarly, for dy, you can differentiate with respect to theta and respect to phi, this function over here, Differentiating with respect to theta gives you cosine theta cosine phi, and differentiating with respect to phi gives you negative sine phi and sine theta d phi. And then similarly dz, well, there's no theta component over here, so you get cosine phi d phi. So over here, I mean, you can kind of see that if you are at this point and you move in the direction of theta, then that doesn't change the z-coordinate. And if you move in the phi direction, then that changes the z-coordinate by cosine phi. Because if you're near the plane, for example, then if you change in phi, then you're moving completely in the z direction. But if you're very near the poles, then you're moving mostly horizontally and not very much vertically. So this does match the intuition of saying that you pass in a vector and tells you how much does the z-coordinate change in that vector's direction. Okay, so now the next step to do is to essentially compute each of these guys in terms of d theta and d phi. And again, this will later be seen as a general procedure called the pullback. But for now, we'll just use the explicit formulas of plugging these in and rearranging things. So this guy is the z-coordinate. This over here is our expression that we found for dx. And this over here is the expression that we found for dy. And that gives us z dx dy, which is the third term over here. So now what we can do is, as I said, if you need to multiply forms together, which is essentially taking the wedge product, then you need to expand by linearity. And so what we get is sine phi times something involving d theta and d theta, something involving d phi and d phi, and then two terms that we actually care about. So the theta d theta term, essentially because this looks like locally looks like an epsilon 1 wedge epsilon 1 is 0. This locally looks like an epsilon 2 wedge epsilon 2, so that's also 0. And then what we're left with is these two terms. So this first one comes from this term multiplied by this term, and the second one comes from this term multiplied by this term. Notice how I was careful to maintain the order of d theta and d phi being multiplied by each other, because these two things are not the same as one another. This one is actually the same as d theta d phi with a negative sign, because remember, this looks like epsilon 2 wedge epsilon 1, which is equal to negative epsilon 1 wedge epsilon 2. So now, because each of these has a d theta d phi 2 form up front, we can factor that out and rewrite that as factor out the theta d phi out here. Notice that both of the terms have a cosine phi sine phi out here, so we can factor that out. Then you have a sine squared theta plus cosine squared theta because of the two negative signs. And then this is just 1, so what you end up with is the sine phi is combined into a sine squared phi and then a cosine phi d theta d phi. And so what this is saying is that if you have this little two vectors over here, which get pushed forward to these two vectors over here, you can either evaluate this 2 form on these two vectors, or you can evaluate this 2 form on these two vectors, and you'll get the same exact answer, which you can try checking for yourself. And so if you want to compute the push forward of these two, what that'll be is taking the derivative of this with respect to theta, and then that'll be the push forward of this vector, and taking the derivative of this with respect to phi, and that'll be the push forward of this vector, holding the other variable constant. Similarly, we can compute y dx dz, which will be the second term, and this is the y, this is dx, and this is dz. And again, we get a sum of things where we have something which looks like d phi d phi, but again, we don't care about it because d phi is going to be equal to 0, and we have d theta d phi, which comes from this term, and then expanding everything out, you have sine squared theta cosine cubed phi d theta d phi with a negative sign. And then similarly, you can compute out x dy dz, which is the third term we have over here, and then we get this expression. So now if you want to compute what omega is, then we just simply have to take the alternating sum of these guys, because that's what we have up here. And we have the omega, which is this minus this plus this, is equal to cosine phi sine squared phi plus sine squared theta cosine cubed phi plus cosine squared theta cosine squared phi d theta d phi, because all these have a d theta d phi in common, so they can be factored out. And then what you'll notice is that we have a cosine squared theta sine squared theta here, so that'll be a 1. And then we can also, I think this should be a cosine cubed phi. And then we can also factor out the sine squared phi and cosine squared phi from the remaining terms. And then what we end up with is a cosine phi d theta d phi. And this should start to look familiar, because this is usually the infinitesimal area form that you get for a sphere. So what this expression says is that if you take these two vectors and then push it forward here, the infinitesimal area spanned by these two vectors is going to be cosine phi times whatever components in the theta and phi directions, push forward. Or you can also evaluate it locally over here, and you can say, okay, what is the area which will be spanned by these two vectors in the image? So what that means is that if you're close to phi equals 0, then this area will, even though these two areas look the same over here, this area will be preserved when it goes into the image because it's near the equator. But this area will be sent near the pole, so its area will essentially be squished down to 0. So this two form is essentially saying it's a different measure of area over here, which is really the measure of area after you look at the image of the two vectors. And so now we can just integrate this normally by taking the integral from minus pi over 2 to pi over 2, and the integral from 0 to 2 pi of cosine phi d theta d phi. And we end up with the answer that we expected, 4 pi. So we can see that, in fact, this procedure, which intuitively, if you pass in the normal vector into the volume form, remember what that means is that it allows us to numerically compute this area by looking at the area of the parallelepiped spanned by those in the normal vector. It does, in fact, give us the area that we wanted.